There is a metal that shouldn't exist. It's stronger than steel, more elastic than titanium. It doesn't rust, doesn't fatigue, doesn't crack the way metal is supposed to crack. It performs so well in golf that regulators banned the club faces made from it. Scientists have known about it since 1960. 65 years, and almost nobody has heard of it, so why isn't it everywhere? To understand why, you have to understand what it's up against. Steel is the foundation of the modern world. Your car, the beams holding up your office building, the pipes under your street, the ship crossing the ocean with your Amazon package. We have used steel in one form or another for 3,000 years. And here is the thing about steel that nobody really talks about. It is full of flaws. Not metaphorically, literally, physically. When you look at steel under a powerful enough microscope, you see something that looks like a mosaic. Millions of tiny crystals packed together, each pointing in a slightly different direction. These are called grains. And where those grains meet, those boundaries are weaknesses. That is where cracks start. That is where corrosion gets in. That is where fatigue accumulates over time until one day the metal fails. It is not a bug exactly, it is just how crystalline metals work. Every metal you have ever touched, whether steel, aluminum, titanium or copper, is crystalline. All of them have grain boundaries, all of them fail along those lines. Every bridge you have driven over, every plane you have flown in, every building you have walked into, all of it is held together by a material with microscopic cracks waiting to happen, managed by engineering rather than solved by it. What if you could make a metal without any of that? No grains, no grain boundaries, no internal structure to crack or corrode along. What if metal could be smooth, all the way down to the atomic level? That's not a fantasy. That's called amorphous metal. Some people call it something better. Metallic glass. The word glass is going to confuse you for a second. Stick with me. Glass, the stuff in your windows, is amorphous. That is not a flaw, it is the defining property. The atoms in glass are not arranged in a regular pattern. They are locked in a kind of frozen disorder, a snapshot of liquid structure that hardened before the atoms could line up into crystals. That is why glass is transparent, why it breaks the way it does, why it feels the way it feels. Now, what if you could do that to metal? What if you could take molten metal, liquid, chaotic, totally disordered, and freeze it so fast that the atoms never had time to organise? No crystals, no grains, no grain boundaries, just smooth, uniform, perfect metal. That is metallic glass. Now here's where it gets strange. Because without grain boundaries, stress cannot concentrate in one spot. There is nowhere for a crack to start. The material distributes force evenly across its entire structure. The result? Many bulk metallic glasses can be roughly twice as strong as conventional steel by weight. The elastic limit, how far it can bend before it stops bouncing back, can be up to 10 times higher. It does not rust the same way. It does not fatigue the same way. And when it is manufactured, it can be moulded into precision shapes with a surface finish so smooth you almost do not need any machining afterward. It basically slides out of the mould, like glass. You know that feeling when you read about a material and think, wait, why isn't everything made of this? That feeling is completely justified. And in a few minutes you're going to understand why this material, and dozens like it, keep hitting the same invisible wall. And why that wall says something uncomfortable about how civilization actually makes decisions. But to understand the wall, you first have to understand what is hitting it. Here is the thing about engineering, you almost always trade one property for another. You want something strong? Fine, but it will be brittle. You want something flexible? Okay, but it will be weak. You want something corrosion resistant? Great! Prepare for it to be expensive, heavy, or both. Engineering is a negotiation. Metallic glass does not play by those rules. It has higher strength and higher elasticity than steel. Most materials pick one. Think about that. Most materials negotiate. This one does not. It has superior corrosion resistance without coatings because there are no grain boundaries for corrosion to penetrate. It has near net shape casting, meaning you can mould it into complex, precise shapes with almost no finishing required. Steel requires massive machining after casting. Metallic glass does not, and because it is so elastic, it stores and releases energy extremely efficiently. You hit it, it does not deform. It hits back. Remember the golf story from the top? Here is what actually happened. Callaway and TaylorMade built driver faces from a zirconium-based metallic glass alloy called liquid metal. The face would flex on impact, store the energy, and return it to the ball more efficiently than steel or titanium ever could. The performance advantage was so large that regulators did not adjust the rules. They pulled the material from competition entirely. This is not a marketing claim, this is a governing body deciding a metal was too good to be legal. It is not just golf. Apple licensed liquid metal for components requiring extreme dimensional precision. Surgeons use metallic glass blades that hold an edge longer than steel and can be ground sharper than anything conventional metal can achieve. In every case, the story is the same. Wherever tolerances are tight and performance actually matters, metallic glass wins. So why has this not changed the world? Because everything I've described, the strength, the elasticity, the precision, the corrosion resistance, all of it is real. The papers are real, the lab results are real. Hundreds of researchers across decades have confirmed these properties. And yet metallic glass is not in your car, not in your building, not in your bridge. It is not widely deployed. There is a wall. Problem 1, the cooling rate. To make metallic glass, you have to cool molten metal extraordinarily fast enough to outrun the atoms and lock them in place before they can organize into crystals. For decades, this meant you could only make metallic glass in very thin forms. Ribbons, wires, thin sheets, anything thicker, the inside of the material cooled too slowly and crystals would start forming before you reached the center. The technical term for the maximum thickness at which a metallic glass can still form is critical casting thickness. For most alloys discovered in the early years, that was fractions of a millimeter. You cannot build a car frame out of a film thinner than a human hair. Even where metallic glass can be formed, it has a real limitation. Under certain loading conditions, particularly shear, it can fail suddenly along what are called shear bands, without the gradual deformation steel would show. It is not fragile, but it is not a straight swap for steel in every application. Engineers have to design around it, so it has limits. Every material does. The difference is that metallic glass limits are manufacturing problems, things humans might solve. Steel's limits are physics, they are permanent. Problem 2, the alloys. Modern bulk metallic glasses, the ones thick enough to actually be useful, use exotic combinations of metals. Zirconium, hafnium, beryllium, palladium. Beryllium in particular is expensive, relatively rare, and genuinely toxic to work with if you are not careful. Palladium-based metallic glasses have extraordinary properties, and palladium costs more per kilogram than gold. You cannot make a structural beam out of something that costs more per kilogram than gold. And then the trap that nobody talks about, scale. Civilization is built around steel. Every steel mill, aluminum smelter, stamping press and machining center on the planet was designed for crystalline metals. The supply chains, the workforce, the capital equipment, all of it, trillions of dollars of infrastructure, built over a century, optimized for a material that metallic glass would need to replace. Metallic glass doesn't just need better factories, it needs a different world. And here's the thing about the world, it does not like being asked to start over. The best material doesn't win, the material that can scale wins. So even as the physics and the lab results keep saying metallic glass is superior, the industry keeps reaching for steel, not out of ignorance, out of inertia. Switching costs are real, retooling is expensive, and steel, for all its flaws, ships on time. Good enough at scale beats extraordinary in a lab, every time. If that sounds abstract, look at any keyboard, a layout designed in the 1870s for mechanical typewriters. The keys were deliberately arranged to slow typists down because early typewriters would jam if you typed too fast. The jamming problem was solved over 100 years ago. You're still using the layout designed around it. In 1936, a man named August Dvorak patented a keyboard layout specifically engineered for human hands. Keys were placed for efficiency, common letters on the home row, fatigue reduced, speed increased. Studies showed typists on Dvorak layouts were measurably faster and made fewer errors. The world did not switch, not because QWERTY was better, because QWERTY was everywhere. Every typewriter, every typist, every office, every school. The cost of switching, retraining millions of workers, replacing millions of machines, rebuilding an entire ecosystem of muscle memory was greater than the benefit of a better layout. QWERTY won because it got there first and built the world around itself. Sound familiar? This is not an accident, it's a pattern. And once you see it, it's everywhere. Steel is QWERTY at civilizational scale. Metallic glass is not the only material in this situation, it has company. Graphene won the Nobel Prize in 2010. In laboratory measurements, its intrinsic strength is hundreds of times that of steel per unit weight. It conducts electricity better than copper, and it conducts heat better than diamond. We've been promised the graphene revolution for 20 years. Your phone doesn't have a graphene battery, your car doesn't have a graphene frame. Manufacturing it at scale, defect-free, at a cost that makes sense, remains unsolved. Carbon nanotubes are theoretically the strongest material ever conceived, roughly 100 times the tensile strength of steel at a fraction of the weight. In 1991, serious researchers with serious funding believed this was a decade away from changing everything. Mildred Dresselhaus, one of the most decorated materials scientists of the 20th century, spent decades pushing carbon science forward. She died in 2017. The manufacturing problem was still unsolved. 3 decades later, it still is. Diamond nanothreads were discovered in 2014. Their theoretical strength makes carbon nanotubes look modest. They remain almost entirely confined to laboratory quantities so small you can barely see them. Do you see the pattern? There is a gap. A massive, frustrating, decades-long gap between discovering that something is extraordinary and actually using it, and this gap doesn't get the attention it deserves. Because we love the discovery story. The discovery is clean, it's exciting. It fits in a headline. Scientist discovers material stronger than steel. That's a great headline. Scientist discovers material stronger than steel, but cannot manufacture it cost-effectively at the scales required for meaningful adoption. And furthermore, the entire industrial ecosystem is optimized for a competing material. That headline does not make the front page, but it is the true story, nearly always. The future of materials science is full of incredible things, and most of them are stuck. Not because the science is wrong, because the world they would have to enter is brutally, obstinately, and expensively already built. Metallic glass is starting to find a way through. So where does metallic glass actually stand? Not dead, not stalled. Making real ground, just not where most people are looking. In fact, metallic glass is already deployed at genuine industrial scale in one place almost nobody talks about. Thin amorphous ribbons are used as transformer cores in electrical grids. They dramatically reduce energy loss compared to conventional steel cores. Millions of them are running right now, quietly doing exactly what the material promises. Iron-based and copper-based alloys are replacing the exotic beryllium and palladium formulations, cutting material costs dramatically. And additive manufacturing, 3D printing with metallic glass, is starting to sidestep the cooling problem entirely. Instead of racing crystallization across a large casting, you build layer by controlled layer. Tiny, repeatable, precise. You are not fighting the physics anymore, you are rooting around it. The wall is still there, but there are doors in it now that did not exist 10 years ago. Which raises the real question, not whether metallic glass will break through, but what it means for us, and for every material like it, that the wall existed at all. We think technology progresses in a straight line. Discovery, development, adoption, the world changes. But that is not how it works. Discovery is the easy part. There is a finish line. You can measure it, publish it, celebrate it. Adoption is a war against inertia, against every factory already built, every supply chain already running, every engineer who already knows a different way, the accumulated weight of every decision that came before. Steel won not because it was the best possible material, it won because it was good enough, early enough to build the entire world around it. And once the world is built around something, the bar for replacing it is not, are you better? The bar is this, are you so much better that it is worth rebuilding everything? Metallic glass is not there yet. Neither is graphene, neither are carbon nanotubes. Maybe they get there, but they will not get there on the strength of their properties alone. They will get there because someone solves the manufacturing problem, the cost problem, the scale problem. Discovery gets headlines. Manufacturing decides history. Because the miracle is never the material. Metallic glass is extraordinary. It has been sitting in our laboratories for 65 years, tantalizingly close to changing everything. Not because it does not work, because the world was already working.